Well, hello there. Today we're starting this class on basically how to solve problem and what does that mean in theoretical computer science. The beginning of the class, and we will talk about algorithmic problems, so problems you basically can solve on a computer. And then by the end of the class we will move on to some other definitions of a computational problem. So something that is not suited for the computer and is not analyzed in terms of how to solve it on a computer, but rather in a different computational models, which will then bind back to algorithms by using clever tricks from these other models in the actual application to algorithmic world. All right, so today we are talking about what is algorithmic problem, how to solve it, and can we be clever when we do that. Algorithmic problem is basically some input that is corresponding to some output. So there is a question and you have to find some answer to it, right? And it is not our goal to get the answer. As a computer scientist, we need to analyze the best possible way to get this answer. So while the problem stated about finding answer, the problem itself is the object of our study, rather than the question that we have to answer. Right? So here is an example. You have a list of numbers. And the question is, are there the three numbers that sum up to 0, right? So this is what I wrote here is an instance of a computational problem. So the problem in general, that there is an array of numbers. There are n numbers. They are all in some suitable range which should be specified, right? Typically in problems like this we say that, hey, they're small enough so we can make arithmetic computations on them in our computational model in constant time. So we have an array of n numbers, and the question is, are there three that sum up to 0? And this is an instance of this problem where n is equal to 6, right? And the answer is yes. How do we know this? Well, you have this one, and this one. Those three numbers, they sum up to 0. This is the answer to this instance. But what we are interested in is how fast or how few resources can we spend while answering this question, right? So while n is 6, it's rather trivial. You can just do it in your head. But when just always think that n is something like billions, and you actually need to spend quite a bit of time to do this. For example, this problem has a trivial solution and has some clever solution. And the trivial solution is, this is basically the focus of today's lecture, right? So the trivial solution is also called a brute force. So you can assume yes. So basically, like, you don't want to think at all. You just wanted to use your muscles to solve a problem, right? So how can you solve this problem without like having a headache of actually doing anything smart? Well, you just pick 3 numbers, check if they sum up to 0. Then you pick another 3 numbers, check if they sum up to 0. And you do that until you run out of triples. So that means that, so this problem called 3-sum problem. And we know that it is solvable in order of n cube. So what does that mean? It means that, well, if you want to go through all the triples, there are n choices of the first number, n minus 1 choice of the second number, and n minus 2 choices of the third number. And this is basically n cube, right? For all the purposes, this is the same as just n cube, so we write that it's order of n cube. This thing has a very formal definition, and I'm absolutely sure that if you're not familiar with it, it will be covered in some other class. I don't really want to cover this in this. Just it's very intuitive. So we always have this trivial solution by just try all possible candidates and then check which one of them will be the right one. But sometimes it's not very clear what is the candidate, or there might be a different ways to think about the problem and the candidates for the solution, because there are different ways to represent the solution to the problem. So this is the notion of a search space. So basically, when you have your problem, you have this space of things that could be a solution. So you want to find something, and you have all the set of all possible things that could be that thing that you are looking for. And the clever thing here is that it's not a built-in thing in the definition of the problem. The search space is something we invent as people who are trying to solve the problem. So here's an example. So a problem called Primality Testing. So you're given a number. So input a number between 1 and n. A number x. Output is x a prime number? So this is a question, right? And what we are looking for is to define a space of things that will certify that x is a prime number, right? And this is kind of hard, right? It's a lot easier to explain why x is not a prime number rather than what it means to be a prime. So the question that we're asking here is x a prime? Could be like there is very little work to get answer to this question from the question is x not a prime, right? So instead of asking is x a prime, we can ask if there is a number that divides x, that is not 1 or x itself. So let's redefine that, right? So this is basically the same problem, just with the answer flipped, right? Is there a number y? Y has to be more than 1, strictly less than x, right? Such that y divides x. So this is a lot better because now our question is about finding something, and when we find it, it's easy to check if this is the correct thing we are looking for, right? So if I'll give you the y, you will verify that y is indeed the witness of x not being a prime by just trying to divide x by y and see that it's not possible, right? So this is usually the form that is most convenient for our computational problems. This is what's called an NP problem, which again we don't want to go into hard definitions because I assume that you will get the formal complexity class later on. But this is the most convenient form of a computational problem you will be dealing in algorithmic classes. So, what would be the brute force solution? How can we solve this problem? So, one way to do this is say, hey, let's go through all the y's and check if they divide x. Right? It's pretty straightforward, right? So we will spend basically linear time in n. Right? So if x is close to n, then you will have to go through all the numbers from 1 to n. So if the answer is yes, there is such a y, maybe you'll get lucky and you'll find this y early on and you will stop. But if x is actually a prime, you will need to get through all the numbers to actually check that. So your time complexity, that is the time you spend on solving this problem, would be linear in n, which is actually like really bad, because linear in n that would mean that the exponential in the size of the description of the problem, and that is usually a lot more than you can afford to spend. That's horribly bad. So how can we redefine the search space? So I still want to stay in this like brute force world, right, where I just go through all possible candidates. I don't want to do any like blows and whistles, but I want to redefine the space such that it would be easier to go through it. Well, there is a rather simple idea. So let's say x is not a prime, right? So suppose x is equal to a product of y times z, right? And both of them are not 1 and are not x itself. I'm claiming then, well, one of them would be no more than square root of x, right? So that means that either y is less or equal to the square root of x, or z is less or equal to the square root of x, which is no more than square root of n. So why is that? Well, suppose that is not true. Suppose both y is more than square root of n and z is more than square root of n. Well, then their product is more than n, which means it cannot be x. That's a pretty straightforward explanation. So that means that one of them is no more than square root of n. That means that in our algorithm we can focus on only finding y that is less or equal to a square root of n, or square root of x if it matters, right? So while we're still asking the same question, we can just reduce the search space from all the numbers from 1 to n to all the numbers from 1 to square root of n. Basically reducing the complexity from order of n to order of square root of n, which is amazing because like we didn't do a thing. We just say, hey, how about you stop after just square root n steps rather than n steps. And that is the power of like cleverly designing the search space. Just sometimes a little bit of thinking will get you pretty far from what original brute force was suggesting, right? So yeah, let's look at another example. Here's another example. So suppose we have a graph, right? So we have a graph and the question is this graph three-colorable? So can you assign a color to each node such that every edge is connecting two nodes with different colors? So there is no edge that connects nodes with the same color. All right. This is a problem which we don't know how to solve in polynomial time. Polynomial basically means efficient and possible in practice, if you'd like that. On the contrary from the previous example, where actually the primality testing we know how to solve in polynomial time. It's a complicated algorithm. We will not cover it now for sure, but it is possible. So you can do a lot better than we did in a few minutes ago. But for this problem, we actually don't know a really fast algorithm, but let's try to get at least something. So 3 colors problem. So your input is graph G, output is its chromatic number of G, at the most 3. So, one way to solve this problem would be to just try all possible colorings of this graph, right? So, if your graph has n nodes, and there are 3 possible colors you can color each node in, it's not hard to see that the whole graph can potentially have up to 3 to the n possible colorings. So we can go through every single one of them and check that the graph is, if the coloring is a correct one, right? That there are indeed no 2 nodes that are connected. So this is clearly a way to do this. The question is, can we do better, right? Can we do better? And the answer is yes, yes we could. Yes, we could do better. So how about we'll do a 2 to the n algorithm rather than 3 to the n. It might seem to be roughly the same, but the difference between like 2 to the 100 and 3 to the 100 is enormous. It's like both numbers are incredibly large, but like it might be possible to do 2 to the 100 on like a supercomputer in some enormous time, and 3 to the 100 is just unimaginable that we can ever do computations like that, right? So how could you get a 2 to the n algorithm for this? Well, let's not color all the nodes at the same time. Let's go one by one, right? So let's take, for example, this one, right? It can be colored in any color, but clearly, if it is our first choice of a node, it doesn't matter which color we color it, right? Regardless of our choices, we will still be, if the graph was 3-colorable, if we change the color of this node, nothing will change, right? It might change the the resulting coloring from what we originally had in mind, but it doesn't matter. So we can color this one in color 1 and not do like any choices here. Okay. But then we can take a look at this node, right? And we already know that this node cannot be color 1, right? Because it is a neighbor of the node with the color 1. So we have two choices. It's either 2 or 3. Okay, so we'll try both possibilities. Let's try 2 first, right? And then we can check again any node that has any neighbor that is already colored. So we can take this one. It already has a neighbor with a color 2, so it can be 1 or 3. So, well, let's check 1 first. And then we can check this node, for example. Again, I'm just arbitrarily picking a node that has a colored neighbor. So this one already has a neighbor of a color 2 and a neighbor of a color 1. So it has to be color 3. There are no choices here. So my point is that every time we're picking a node that already has a colored neighbor, there are at most 2 possible choices for this node, right? And I'm also claiming that, well, we always be able to pick a node with that already has a colored neighbor, unless our graph is disconnected, right? So theoretically, it was possible that our graph doesn't look like this; it looked like this. So you have 2 different components, but then again, after you colored this whole thing, you will move on to color this one, and for this component, we can also pick a node that has no colored neighbors, but this is the first node in this component, right? So we can color it whatever the color we like. We can color it the first color and have no repercussions. So we can do this for free. So if you go through the calculations, if you have n nodes, the very first node in every component, we colored it in color 1. Then we go through the neighbors of the colored nodes, and we have at most 2 choices. Sometimes we have just 1 choice. And sometimes, for example, if we already colored this one before this one, if we color it with the color 3, then this one has 0 options, right? That means that this branch of computation is over, and we don't want to talk about it anymore. So we just discard this whole previous coloring as bad. Okay. So we have at most 2 choices for everyone. So the whole running time would be something like 2 to the n. Again, I'm trying to give you more of an idea of different approaches to computations rather than very strict proof of complexity, and I don't want to do the refinement of this. So this symbol means something like that, right? So it's roughly equal to 2 to the n. So yeah. All right, so this is one way to do this, but I actually want to go through another algorithm that gives you 2 to the n, which is always great because it's not about that there is a perfect solution for perfect algorithm or perfect solution or perfect, trick that will solve your problem. Sometimes you can get the absolutely different solutions that will end up having the same running time and the same everything, and this is part of the fun in this area. So again, we are aiming for the 2 to the n algorithm, but we'll do it in a style of these search spaces that we've talked earlier about. All right, so first let's dial it back a little bit. So I want to first look at the 2 coloring problem. So can you color a graph with just 2 colors? And surprisingly, this problem is just a lot simpler than 3 coloring, exactly because of the style of algorithm that I just described. Right? You pick a node, you color it with the color 1, then all of its neighbors have to be of the color 2. Then all of their neighbors have to be of the color 1, and so on. So in this case, this graph is obviously not 2 colorable, so this one would be of color 1, this would be of color 2, this guy will be forced to be of color 1, and then this guy doesn't have options at all, so that's it. In this case, it's not about that this branch of computations is over, it's all over, right? We don't have different choices. We just have one path, right? So we're just going through this graph and color nodes, and if we fail to color 1, that's it, graph is not 2 colorable. If we get to the end and color everything, then the graph is 2 colorable. So this whole thing can be done in linear time, or roughly linear time. So we can solve 2 coloring problem in time. In time linear in the size of the graph. Why does it matter? First of all, it's kind of fun to notice that the problems that look very much the same, like what can be the difference between 2 coloring and 3 coloring, can have such a drastic difference in computational complexity. So this one can be solved in linear time in the size of the graph, and the 3 coloring, for what we know, is require exponential time in the size of the graph. So this is a simple problem. 3 coloring is a very hard problem. But how can we use 2 coloring to solve 3 coloring in a little bit less time? So let's go back to the 3 coloring, and I don't want to deal with this graph anymore. So instead of looking at this question, so this question, what is it we are looking for? We are looking for a coloring, and as we said at the very first thing, that there are 3 to the n different colorings that can be used in a graph. So the brute force without any modifications will run in 3 to the n, because this is a form of a question that we have chosen. So what would be another form of a question that can be applied here? So this is equivalent to there exists an I which is an independent set of G such that G minus I, so G with that independent set throwing out, has chromatic number at most 2. So what does that mean? So we're taking our graph G. If it is 3 colorable, that means that we can divide it into 3 parts, right? Part 1, part 2, and part 3. Each consists of nodes with that color, and then the definition of the properly colored graph means that there are no nodes between no edges between the nodes in each part, right? So there are no edges inside this part, no edges inside this part, and no edges in this part, right? So all the edges going only across those borders. So if I can find an independent set, suppose we can take the independent set that forms the first color in the proper coloring of my graph, right? Then the rest of the graph obviously is 2 colorable, right? So we can color this part with color 2 and this part with a color 3. So this will satisfy that our graph is 2 colorable. So that means that after we take this independent set, the rest is 2 colorable, which is exactly the definition of my question. So those 2 things are just equivalent. That's what I want to point out. That in that is just this very same question. So why this question is better than that one? So the search space is a lot smaller. Because what is the search space here? It's all possible independent sets of G. How can we go through all the independent sets of G? Well, we can just enumerate all possible subsets of nodes of G. Check if there is an edge inside the subset. So there are 2 to the n possible subsets of nodes. And for each of them, it's really easy to check if it's indeed an independent set. And if it's an independent set, then we also can ask the second question, is the rest of the graph 2 colorable? Which we know we can do. We can answer that in linear time. So we can answer the question for every candidate in some small time compared to the number of the candidates. So the dominating term in the running time would be that the number of the candidates, which is 2 to the n. So we're checking independent sets. We're checking just subsets. For each subset, we check if it's an independent set and if the rest of the graph is two-colorable. And this is great. But is it better than the algorithm that we discussed before? Well, yes. Yes, it is better because it could be improved, right? So we can use absolutely the same idea as we did with the primality testing, right? With the primality testing, we said, hey, if our number has a divisor, this divisor couldn't be too big because otherwise it wouldn't work. So the same goes for this partition into independent sets. If I have 3 independent sets that together form my graph, then, well, one of them has to be smaller than n over 3, right? So I can ask the same. So instead of asking this or this, I can just add another condition, and size of I is less or equal to n over 3. So we are not just picking any color now to check that the complement of it is two-colorable. We are now looking for the smallest one. And if you check how many candidates there are now, it would be actually smaller than 2 to the n. I don't want to go into precise calculations of how to do that, but if you ask this question and do the brute force through the search space, you will have roughly 1.9 to the n possible candidates. So again, by just adding just a little bit more thinking, just thinking about our search space just a little bit more, we get a better solution, a better algorithm, a better running time. And that is still just the simplest possible algorithmic paradigm. So you define a search space, you go through all possible candidates, you check if they satisfy the properties that you write for them. That's it, basically, right? All right. So this is one way to solve problems. This is clearly not the only way. If that was all we have to offer, that wouldn't be a fun class, right? So how else can you solve problems? Among all the possible ways to do clever tricks, one I find particularly fascinating is what's called dynamic programming. So the idea is that you solve sub-problems of your original problem. And you start with very simple sub-problems, and you let the complexity of these sub-problems grow. But every time you solve a sub-problem, it relies on the already computed results, right? So The simplest example of such would be computing of Fibonacci numbers. So the definition is that phi 0 is 1, phi 1 is 1, and phi k is equal to phi k minus 1 plus phi k minus 2. So the sequence goes as 1, 1, 2, 3, 5, 8, 13, and 21, and so on. So you can ask what is the nth Fibonacci number, right? So how would you do that? Well, clearly you have this definition, right? So to compute phi n, you need to compute phi n minus 1, right? And then you need to compute phi n minus 2. And if you do that, you'll find yourself with a horrifyingly slow exponential type algorithm, right? Because to find this one, we will need to find this one and this one. This will try to find this one, we will try to find phi n minus 1 and minus 2 plus phi n minus 3. So now we already have 3 things we need to compute. But now to find this one, we need to find phi n minus 3 plus phi n minus 4. So now we have 4 things we need to compute, and so on, right? So you will actually have like this horrifying time complexity, like something like 1.7 to the n if you do it this way. But obviously, like it's something you can notice immediately when you look at what this algorithm is doing, but something you might miss if you just try to code it, right? So you can just code it like this and say, hey, this is good enough. But if you think about it for a second, you will notice that, hey, when I'm computing this one, I want to compute this one and this one. But I already want to compute this one. So at this point, I want to compute the same thing twice, which doesn't make any sense, right? This is just unforgivably inefficient to actually just try to find the same thing twice. Come on. So what you do instead, you don't do that. You don't just say, hey, I have a definition of what phi n is. Instead, you start small, right? So you compute phi 0, phi 1, phi 2, and so on, until you get to the phi n minus 1, phi n. So computing every single one of them is easy because you already know the previous results, right? So that sequence that I wrote over there at the top, this is exactly what your algorithm will be doing. So instead of going backwards and just, slam your head against the wall because I know that I want to compute phi n, and I have the formula for phi n. So I will do that until I die. Instead, we start small and we just build up our intel about this whole Fibonacci sequence until we'll be able to use that information to actually use the formula to actually get the phi n. And this is the essence of the dynamic programming approach. I know this is not the most exciting example, but this is exactly what we want to do here. We want to slowly increase our understanding of what we're dealing with by having these like small incremental steps. And at some point we'll have all the information we need to actually answer the question that we were looking for. All right, let's do something a little bit more fun. All right, so here is a problem. Longest common subsequence. Or short for LCS. So your input two sequences of n things. It could be numbers, it could be letters. Let's say letters so you have two sequences of letters or strings, and so you have your A and B, both n letter strings. And your output should be size of LCS. So what is the longest common subsequence for those two strings? And this is a fun example because it is just unimaginably bad if you try to solve it using the brute force, right? So yeah, it's just really bad idea to try to do that. So try to select like a sequence from the top. That would be like something like 2 to the n choices of the sequence of a subsequence, and then for each of them you need to check if they're a subsequence of the other string. So let's do something fun instead. So let's use our dynamic programming approach. Okay. So what I have is two strings, and I want to find the longest common subsequence, right? And as I said, our dynamic programming is about gradually increasing our understanding of the situation. So instead of jumping into this question straight ahead, we can ask this question about just the first letter of this string and the first letter of this string, right? And that's simple, right? So we're talking about just a longest common subsequence of two strings, each has just one character, just one letter, right? So I have this and this, and there are two possible scenarios. Either those strings are equal, so those two letters are just the same letter, in which case the longest common subsequence is 1, or those are two different characters, in which case the longest common subsequence is 0. So this is our trivial beginning of, gathering this intel. What we'll do next, we'll say, hey, how about this string and this string? And how about this string and this string? So for every two prefixes, for every prefix of the first string and every prefix of the second string, we will try to find what is their longest common subsequence, right? So we will have that Tij is longest common subsequence, size of the longest common subsequence of A from 1 to I and B from 1 to J. And as with example with Fibonacci numbers, right? The whole point is that while this question is not any easier than what we want to ask, right? Because if you put T and N here, you will get exactly the question we want to answer, right? So it's not about this question. It's not about computing Tij is easy. Is that computing Tij is easy if you know all the previous results, if you know all the rest of the Tijs, right? So for example, this one. So let's say this is I, this is J. So we have that. So there are several possible scenarios, right? So one scenario would be that those two characters are equal to each other, right? So this one would be so it would be max between three different options. So First of all, so if those two characters are equal, then, okay, now let me put it this way. So if AI is equal to Bj, then this whole thing I'm claiming is equal to 1 plus Ti minus 1 J minus 1, right? So this is not too hard to see, right? So we can match those two and say, hey, those two are the same character, and there is no reason not to match them in a sequence, right? So, and then we need to say, hey, if those two are matched in a longest common subsequence, then before that we can use just the longest common subsequence for these prefixes without the last character. So Ti minus 1, J minus 1. So in another option is if AI is not equal to Bj. Well, then we also have our options. So we know those two are not matched together. And that means that at least one of them is not used in the longest common subsequence. So either this character is not used or this character is not used, right? It couldn't be that they're both used, otherwise we will have a situation like this. And we cannot have, it is not consistent with the definition of common subsequence, right? So they're not, it's not what we're looking for. So we know that at least one of them is not used anywhere. So you can say that it's max between Ti minus 1j, which means we don't use the ith character of the first string, or Ti j minus 1, which means that we are not using the jth character of the second string. And if we didn't know what are those numbers, if we try to go from what we need to know, right? So we can do it recursively. That will give you exponential time algorithm, which again we don't want to have. Instead, we start small and just build up, because we already computed Ti minus 1j, Ti j minus 1, and Ti minus 1 j minus 1. We can compute Tij in a constant time, which means that our time complexity of this problem, so our algorithm will run in time to just fill in this whole table for all I and j, and then we can just answer with the value we'll find in T and n. So the whole thing is computable in n squared time, because that's how many different combination of I and j there can be. So yeah. Well, I hope you enjoyed it. The next lecture will go over some randomized techniques in algorithms, and yeah, see you soon.